When students have become fluent with multiplication within 100, it is important to consolidate their understanding of the crucial role of 10 in the decimal number system. Learning to count multiples of 11, 12, 13, 14, and 15, and understanding their relationship to multiples of 1, 2, 3, 4, and 5 will help prepare students to use decomposition strategies in multiplication and division. Let's begin by reviewing the patterns in the multiples of single digits. First, let's count by 1 to 30, but only say the ones. Do not pronounce the tens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. This exercise helps students to focus on the structure of the decimal or base 10 number system. Incidentally, it can also help students to understand that the base 10 number system would not be possible without the digit and the concept of 0. Now let's try an exercise that may at first seem more challenging. Let's count by 9 to 180, again only saying the ones. 9, 8, 7, 6, 5, 4, 3, 2, 1, 0, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Did you notice something special about the pattern of ones in multiples of 1 and 9? Both use all 10 digits in the base 10 number system, but the multiples of 9 are in declining or reverse order. This is because 1 and 9 make 10. In any pattern of multiples, tens are denoted by 0 or the absence of ones. Now let's count by 2 to 30, again only saying the ones. 2, 4, 6, 8, 0, 2, 4, 6, 8, 0, 2, 4, 6, 8, 0. In a sense, counting by 2 is the same as counting by 1 using only the even digits. This pattern may also help students to understand why 0 is an even number. Can you make a prediction about the pattern of ones in multiples of 8? Let's count by 8 to 80, only saying the ones. 8, 6, 4, 2, 0, 8, 6, 4, 2, 0. Did you predict that the number of ones in multiples of 8 would be the even digits in declining order, with 0 as always denoting tens? Again, this pattern arises because 2 and 8 make 10. Now let's try an exercise that really is somewhat challenging. Let's count by 3 to 60, only saying the ones. It helps if you use the decomposition strategy we have learned and separate the ones from the tens in your mind, focusing on the ones. Because this is somewhat challenging, we'll slow it down a little bit. 3, 6, 9, 2, 5, 8, 1, 4, 7, 0, 3, 6, 9, 2, 5, 8, 1, 4, 7, 0. It should be easy to see why counting by 3 is more challenging than any of the other counts we have done so far. Because 3 is an odd number, it uses all 10 digits of the base 10 number system. However, unlike multiples of 1 and 9, the digits are not in order. The order of this pattern is easier to remember if you think of it as 3 subcounts, starting with 3, 2, and 1. 3, 6, 9, 2, 5, 8, 1, 4, 7. Then we have a 10, and the pattern repeats. By now, you have probably figured out that it is also challenging to count by 7. Let's try it to 140. Again, it helps if you use the decomposition strategy and focus on the ones. 7, 4, 1, 8, 5, 2, 9, 6, 3, 0, 7, 4, 1, 8, 5, 2, 9, 6, 3, 0. Of course, this pattern is the reverse of multiples of 3. Again, it may help to remember the pattern to think of it as 3 subcounts, beginning with 7, 8, and 9. 7, 4, 1, 8, 5, 2, 9, 6, 3. Then we have a 10, and the pattern repeats. Can you make a prediction about the pattern of ones in multiples of 4? Let's count by 4 to 40, only saying the ones. 4, 8, 2, 6, 0, 4, 8, 2, 6, 0. Did you predict that the ones in multiples of 4 would use all of the even digits but not in order? This pattern is not as easy as the pattern in 2 or 8, but is certainly much simpler than the patterns in 1 and 7. Because 4 and 6 make 10, the pattern of ones in the multiples of 6 will be the reverse of the pattern for multiples of 4. Let's count by 6 to 60, only saying the ones. 6, 2, 8, 4, 0. 6, 2, 8, 4, 0. We have seen that the pattern of ones in multiples of 1 consists simply of the 10 digits that make up the base 10 number system. The pattern of ones in the multiples of 9 consists of these same 10 digits in reverse order, except that 0 still comes last because 0 ones denotes tens. The pattern of ones in multiples of 2 is similar to that for multiples of 1, except only even digits are used. And the pattern of ones in multiples of 8 is the reverse of the pattern for multiples of 2, except again, 0 always comes last because it denotes tens. We have also seen that the pattern of ones in multiples of 3 and multiples of 7 use all 10 digits in the base 10 number system, but not in order. Because these patterns are more complicated, it is more challenging to count by 3 or count by 7, and it can also take longer to master multiplication facts that involve multiples of 3 and 7. Similarly, the pattern of ones in multiples of 4 and 6 use all of the even digits in the decimal number system, but not in order. Finally, we have seen that the pattern of ones in multiples of 9, 8, 7, and 6 is the reverse of the pattern of ones in multiples of 1, 2, 3, 4. Because the decimal number system uses 10 digits, whenever we get to a 10, we unitize and mark 0 ones, then we repeat starting at 1. That is why each pair of digits that make 10 use the same pattern of ones in their multiples, except in opposite orders. We have not discussed the patterns of ones in multiples of 5 and 10, but by now it should be easy to see why counting by 10 and mastering multiplication by 10 is easy, and counting by 5 and mastering multiplication by 5 is almost as easy. Can you use what we have learned about the patterns of ones in multiples of the digits that make up the base 10 number system to make a prediction about the pattern of ones in multiples of 11, 12, 13, 14, and 15? First, let's count by 11. 11, 22, 33, 44, 55, 66, 77, 88, 99, 110, 121, 132, 143. What do you notice about the multiples of 11? First, the ones follow the same pattern as the multiples of 1. They are the 10 digits that make up the decimal number system in order, except that 0 is last. Then the pattern repeats. They are also similar to the multiples of 9 because they are on a diagonal. However, the diagonal for multiples of 11 runs in the opposite direction. This is because 9 is 1 less than 10, and 11 is 1 more than 10. Now let's count by 12. 12, 24, 36, 48, 60, 72, 84, 96, 108, 120, 132, 144. What patterns do you notice in the multiples of 12? The ones use the even digits in increasing order, just like the multiples of 2. They are also on a diagonal that is very similar to the multiples of 8, except that it runs in the opposite direction. This is because 8 is 2 less than 10, and 12 is 2 more than 10. Now let's count by 13. 13, 26, 39, 52, 65, 78, 91, 104, 117, 130, 143. By now, it is no surprise that the ones in the multiples of 13 follow the same pattern as the ones in the multiples of 3. Of course, this is because 13 is composed of 10 and 3. Now let's count by 14. 14, 28, 42, 56, 70, 84, 98, 112, 126, 140. The ones in multiples of 14 follow the same pattern as that of the multiples of 4, again because 14 is composed of 10 and 4. We can also notice that the multiples of 14 include every other multiple of 7, because 2 7s make 14. Finally, let's count by 15. 15, 30, 45, 60, 75, 90, 105, 120, 135, 150. The ones in the multiples of 15 are the same as the ones in the multiples of 5 because 15 is composed of 10 and 5. In addition, we can see that the multiples of 15 consist of every third multiple of 5. This is because 3 5s make 15. We have seen that the ones in multiples of 11 follow the same pattern as multiples of 1. In fact, the multiples of any number with 1 ones would follow this same pattern. Similarly, any number with 2 ones would follow the pattern of the multiples of 2. Any number with 3 ones would follow the pattern of multiples of 3. Any number with 4 ones would follow the pattern of multiples of 4. And any number with 5 ones would follow the pattern of multiples of 5. Students who acquire a deep understanding of the crucial role of 10 in the decimal number system will have no trouble learning to use decomposition strategies in multiplication and division. They will also be well positioned to generalize their understanding of place value to arbitrarily large and eventually arbitrarily small powers of 10.